So you're here to solve this Nanro by Palmer Mebane called 6 Afraid of 7, which is one of my favorite titles in recent history on the site. If you don't know why, ask a kid somewhere, see if they know. We're going to start on the left where we've got these 7s, and notice that we can't have these 7s crossing over these boundaries. I'm not going to mark in those X's this time, but we also have some fairly compact regions. For instance, we can only take 3 cells of this 2 by 2, 3 cells of this 2 by 2, so that's a total of 6, 7, 8. So this has 1 effective degree of freedom. This region has 1 plus 3 is 4, 5, 6, 7, 8. So again, 1 effective degree of freedom. The 7, if it efficiently packed the top, could get 5 into this 2 by 3, with 5 being 6, 7, 8, again, 1 degree of freedom. And notice that this region share at least these cells as boundaries. So the degree of freedom I have to be losing is one of these cells in blue and one of these cells in red. So everything else around these I can now mark in as forced, including that I have to take 6 up top, including I take these 3. That actually marks off these cells. For connectivity, I have to take this one. For connectivity, I have to take this one. Having marked this cell in green puts in this. That clears up blue and red. This 7 has to come over and take these. It takes 3 of this set, and the shaded cell will be one of these 2 on the left and not those. So this looks like a good start on the left of the grid. And we're now running into a secondary constraint that we can think through in this puzzle, which is we actually have dominoes that are bridging the center divide, where the center divide is a big river-shaped thing that's got a 3 in it. And dominoes have an interesting way. When dominoes touch a domino, you'll get a case where if one of these cells is shaded like this as a 1, anytime you're near a 1, you always have to shade this opposite cell touching it, because if you didn't, you'd have a 1 with a 1. And this can be on or off, that's fine, but we now effectively have this as if it's a 1 or a 2. If it were a 2, it uses this cell. If it's a 1, it always sort of, again, uses a cell. We can't sort of put this into the grid and get a 1 near a 1, so we can do this again. This region can't be of size 2, so it also can't take this cell, because that would put a 1 with a 1. So this is off, this is on. This is a group of size 1. So we've got this start. Still a little bit of work to get through the middle, but let's come and do the counts of degrees of freedom for the 6s. This top 2 by 3 can take 5, 6, 7, so 1 degree of freedom in this region. This can take 1, 3 around this, that's 4, 5, 6, 7, so this also has 1 degree of freedom. Again, here's a space where I'm going to have to shade off 1 in blue and 1 in red to get to a count of 6 in both regions. This will have to be on, this will be on. This has to be efficiently packed. To take 5 up above, that marks off this cell, marks in these cells, marks off this in blue, which puts in this, this, and that shaded. This for 2 by 2 rule is a good start. This now actually marks off this for this bottom region of 6. This 6 started with 8 cells it could use, but 2 of them have been marked off, so we actually have this now as some forced constraints around it. This will have to be a 1. This will be a 1, which means this is a 2. That means this is a 1. Which means we actually do have to always shade this cell. Seeing if there's anything more we know for sure. I think that's a good start. So we've got some beginnings of these connections, but we still have some issues to work through, and maybe now it's time to focus on the big 3. And let's look at connectivity so far in the grid. So there's this boundary, which means this upper right set is different from this lower right set, and that lower right set would really be helped if I take this cell. But somewhere at this cell coming over, or at this cell or at this cell, I'm going to need to come through the center region. I think these 2 in blue are going to be most useful. One of these, at least, is going to need to be taken to make a 3. If these in blue aren't taken, so let's sort of mark both of these off, then the only way I can get this to work is going to be taking 2 cells from the bottom here, and that's going to close off everything else in this grid. So let's see if there's a reason this is problematic, not using one of these 2 in red. And it's probably going to come from looking over to the left and saying, can I get this 7 connected to this 7 down below? And it's going to come from looking at these dominoes. These dominoes have a bit of a push-pull that's not good for them. In one case, if I take this in pink, I can't take this cell. And not being able to take that cell is going to actually isolate this cell on its own. So I would want to take this red, but again, I'm using something which is like through 2 yellows below. So if pink is true and I'm following the yellow path, then I would isolate the cell and there's no more I can take through this middle space. Separately, if this is pink, I mark this off in the grid. And then that means this one is isolated and has to take one of these cells. So long story short, I've got to take at least one of these in red. But even if I take this in red or this in red, I'm not getting all the way through the grid, I don't think, unless I can actually come across this channel. So let's see if I can use this channel. Way to think about that is first, this upper region has to be a 1, and this region is not yet connected down below. So let's say, can this come across and also connect through this 3 in an efficient path? This would have to be a 1, but this can't be a 2 if this is actually used. And if this were a 2, then the 1 has to come up here. We have to take another cell. So there's a functional gap where I can't cross this whole center through just this cell up here, which means I also can't use just this cell or this cell to get across. We need one more that's coming in here, but it's going to have to be effectively joining one of these spaces. And the critical ones we were marking were around these ones and how they were going. So I'm going to need to take 2 of these in red. And I think actually on the surface, you can see this is not an efficient join in red. So I'm going to have to do something through this. I can mark the rest of the cells up at the top, at least as a starting point off. We're going to want to get through connection taking this, which is actually going to want to take through connection this, which puts in a 2. That means this 3 is coming through to the left. This will also want to come down through this channel. So this is 2 if a 1 puts in this 2. This one now is very much where this connection is going to be poised, but let's start by at least doing something to help us out on this side. So this isn't coming through, this forms a 2. We've got an option to take this cell, but then we still have this stranded, so this cell has to be used to actually get this connection to happen. And then we still don't, in this space, have sign that connects to the left, but we're going to have to take one of these 1, 2, 3 cells to get over to the left, so we can mark off the rest. That now means this set through the 7 has to take this cell. That cancels these. It marks in this. The only cell to go that connects to the rest is this, and we cancel out the grids. So pretty hard puzzle, interesting puzzle. The 7s and the 6s on the 2 sides got set up pretty easily, but then left to connectivity constraints. How to get through the grid was really forced with a required and efficient packing. This 3 can't bridge across the top, so we need to take 2 cells somewhere in the bottom to get this side to both join to the upper right and to the whole left of the grid. And working through some of those opportunities, saw where we were taking cells in this middle stretch, and we eventually resolved that down. So hope you got something through this video and hope you enjoyed most of this Nanro week. We'll see you again soon.